Dear students, in this video we are going to derive the governing differential equation for one-dimensional bar elements. Okay, so governing differential equations describe the physics of a problem. Okay, so these governing differential equations will relate the dependent variables and independent variables of a problem. So in the present case, you are considering a one-dimensional bar element. So when it is subjected to axial loading condition, the factors stress, strain and the material property Young's modulus are relevant to the physical behavior of the problem. They will describe the physical behavior of the problem. Okay, so here the independent variable will be the distance. Okay, and the dependent variable will be the deformation. Okay, so to derive the expression for deformation with respect to the distance when it is subjected to loading condition, we should know the governing differential equation of the one-dimensional bar element. So let us discuss how to derive the governing differential equation for one-dimensional bar elements. So this is the problem which you have considered for the derivation. So the one-dimensional bar element of length L is considered. It is distributed along the positive x-axis. It is subjected to a uniform axial load of magnitude Q0. So to derive the governing differential equation, let us consider a very small portion of length dx along the distribution of the bar, which is located exactly at x units of distance from the left portion of the bar. Okay, so certainly the length of the remaining portion will be L minus x, because the total length of the bar element is L units. Okay, so the force experienced by the smaller portion of length dx which you have considered, F, will be the uniform axial load Q0 Newton per meter into the distance L minus x, because whenever we are considering a uniformly distributed load, then to convert it into exact point load, then we will multiply the UDL acting at the portion and the distance of the portion. In the same way, we have expressed the force experienced by the smaller portion. Q0 is the uniform load into the distance L minus x. So we know that the stress induced can be calculated using the formula sigma is equal to force per area. So the force Q0 into L minus x divided by area. And from the Hooke's law, we know that the Young's modulus E can be expressed like this: stress by strain. That is, E is equal to sigma by E. So already we have developed the expression for stress induced. So E is equal to Q0 L minus x by A into the strain component E. So by taking the strain component to the left hand side, then the expression will be like this: EE is equal to Q0 into L minus x by E. So we know the differential form for the strain component small e is du by dx. So we can write like this: E du by dx is equal to Q0 into L minus x by A. So by differentiating once with respect to x, we will be arriving at E d square u by dx square is equal to, in the right hand side, Q0 by A term as a constant value. So we can differentiate the remaining terms. That is, the differential form for L length is 0 minus the differential form for x is 1. Okay, so again by taking the area to the left hand side of the equation, AE d square u by dx square is equal to Q0 into minus 1, that is minus Q0. So then we can simply write like this: AE d square u by dx square plus Q0 is equal to 0. So this is the required result. That is, this is the governing differential equation for a one-dimensional bar element when it is subjected to uniform axial load. Thank you.